Okay, so in the previous class, we have seen the derivation of MOSFET design equation or IDS. Okay. So in that derivation, as per the definition of current, we require the number of charge carriers present in the channel by divided by time. So for number of charge carriers present in channel, okay, we have just taken a few formulas at the initial stage. Q is equals to CV. Okay, then what is C and what is V? Then again, individual terms we have identified and written few formulas. All the formulas we have put in the main equation to get three different equations. One for saturation region, which is nothing but beta by 2 into VGS minus VT the whole square. This is the current equation of MOSFET in saturation region. Okay. Where beta is mu COX W by L. Okay. In the same way, in cutoff, because the device is off, current is 0, and in linear region also we have got the equation. After that, we went through the DC transfer characteristics of the inverter. So in that we have seen the transfer characteristics of NMOS and the transfer characteristics of PMOS in the third quadrant, because we have for inverter PMOS and NMOS. Okay, both the MOSFETs are used in the design of inverter. Therefore, what we do, we just take the mirror image of this and we will shift this graph, or we will overlap this graph here. First we take the mirror image, then we overlap it here. So it will be like this. And then what we do, we take the intersection points. And finally we arrive at the graph of V0 versus Vi, which is in this way. What this graph tells us is, as Vi proceeds towards VDD, as Vi is initially 0, output is VDD. When Vi increases for the inverter, output will start falling. Because for 0 digest it is VDD. For VDD output is 0 because it is inverter. But as we proceed towards VDD, the output will fall. Okay. And say example they have taken, if the input is VDD by 2, then the output is also VDD by 2. So this is the transfer characteristics of inverter, which is plotted in the way like V0 by Vi or V0 versus Vi. This graph is V0 versus Vi. Vi how we change, V0 how it varies. Fine. This we have seen, I think we covered till this point. And we have seen a table. In that table we have the equations. What should be the Vi for cutoff region? What should be the Vi for saturation and linear region for NMOS, similarly for PMOS, and what is V0 for linear region, saturation region for NMOS and PMOS. Okay. In cutoff region, V0 is not valid, therefore we have not written V0. You can check. A table cutoff region is V0 bardila now. Because the device itself is off. Okay. But for linear and saturation, we have mentioned V in V0, V in V0. Next, we are moving towards effect of beta ratio on transfer characteristics. Effect of beta ratio on transfer characteristics. So we know what is transfer characteristics now. This is the transfer characteristics. I'll explain this concept in very simple words. Effect of beta ratio means what? What is beta actually? The derivation we have seen. At the end, we have replaced beta with this term. This term is beta. Okay. And now I am telling the ratio of beta. Okay. Ratio of beta means beta for PMOS and beta for NMOS. Beta for PMOS and beta for NMOS. So if I write this for PMOS, so beta P will be mu P. Okay, COX is a general term. W and L, WP I can write. L cannot be changed. Say if I am working on say 90 nanometer technology. 90 nanometer technology means what? The channel length is 90 nanometers. Means what? The distance between drain and source is 90 nanometers. Okay. Now if I am working on 90 nanometers, that 90 cannot be changed. It is a GPDK which we use, technology 5. Okay. If you are working in 90 nanometers, you will work in 90 nanometers, you can change the width, but you cannot change the length. Lengths are fixed. Okay. So, width can be changed. Fine. So, actually, this is a constant. Mu. Mu means what? Mobility. Mobility of the charge carrier. It is a constant. COX is a constant. COX is a constant. Okay. Epsilon of S. That formula we have. And L is also constant. L cannot be changed. For one technology, L cannot be changed. And if I divide this, say by beta n means what? It is beta of NMOS. This is beta of PMOS. So I'll write here mu of n, then COX, then W n divided by L. Okay, so COX can be cancelled. L can be cancelled because L for PMOS and L for NMOS is same. We just play with only W. Width doesn't change what you know. Okay, and mu P and mu N what it is? Mobility. Mobility of holes, mobility of electrons. Okay, so if we say that mobility of holes is half of mobility of electrons, still these two can be cancelled and 2 can be written here. Like this. So constant terms in other to cancel banana. So I am left with beta P by beta N, which actually indicates width of the PMOS and width of the NMOS. We are studying the beta ratio on transfer characteristics. Andre ಏನು? I'll tell what is that. Beta ratio. Okay. If I change this beta ratio means what? It is always PMOS by NMOS. Beta ratio means it is always PMOS by NMOS. Because we have only 2 MOSFETs. For inverter, I have only 2 MOSFETs. So one is P, one is N. Like this. Okay. So here I can have beta of P and I can have beta of N. And with this, we are studying the effect of beta ratio on this graph. Okay. Andre ಇನ್ನೂ ಸಿಂಪಲ್ ವರ್ಡ್ಸ್ ಒಳಗೆ ಏನು ಕಲೀಲಿಕ್ಕೆ ಅಂದ್ರೆ if I change the width of PMOS or if I change the width of NMOS, how this graph will change? ಅಷ್ಟೇ ಕಲಿತೀವಿ. Okay, so beta mu L ಎಲ್ಲ ಬರ್ಬಿಟ್ರೆ ನಿಮಗೆ ಏನೂ ತಿಳಿದಿಲ್ಲ ಅಂದ್ರು. What we are studying is if I change the width of PMOS or if I change the width of NMOS, how it will affect the graph. Or graph ಅಂದ್ರೆ ಏನು? It just shows the operation of inverter. Okay, so if I change the width of PMOS or if I change the width of NMOS, how this circuit will behave, that we are studying. ಅಷ್ಟೇ ಕಲಿತೀವಿ. Fine. So the beta ಒಳಗ whenever I say beta, you consider it as W by L. W by W only. Beta ratio is beta P by beta L, which can be written as WP by WL, the width of PMOS by width of NMOS. Why it is like that? Because all the constant terms gets cancelled. We are left with only W. W ಜೊತೆ ಅಷ್ಟೇ ಆಟ ಆಡಬಹುದು. We can play with W. Okay. Now, this concept is very simple to understand. Very simple way to understand ಮಾಡ್ಸೋಣ. See, if I make WP more, if I make WP more, andre width of PMOS is more. Okay. If I make width of PMOS more, what will happen? More current will flow. More current will flow. Easy current will flow. At that time, PMOS will become more stronger. Correct? PMOS will become more stronger. If I again increase the width of PMOS, ಇನ್ನೂ ಜಾಸ್ತಿ ಮಾಡಿದೆ, again more current will flow because space is more, so easily current can flow. Right? So PMOS becomes stronger than NMOS. ಹೌದಾ? Understanding? ಇಷ್ಟು ಹೇಳಿದ್ರೆ PMOS ಇನ್ ಬಿಟ್ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ PMOS ಸ್ಟ್ರಾಂಗ್ ಆಗ್ತೈತಿ, NMOS ಇನ್ ಬಿಟ್ ಜಾಸ್ತಿ ಮಾಡಿದ್ರೆ NMOS ಸ್ಟ್ರಾಂಗ್ ಆಗ್ತೈತಿ. ಸ್ಟ್ರಾಂಗ್ ಅಂದ್ರೆ ಏನು? ಇನ್ ಟರ್ಮ್ಸ್ ಆಫ್ ಕರೆಂಟ್ ಪಾಯಿಂಟ್. Right? So PMOS in ಕೆಲಸ ಏನು? What PMOS does? Pull up. This is called as pull up device, right? Remember why it is called as pull up device? What it will do to the output? ಏನು ಮಾಡ್ತದೆ? Why we call PMOS as pull up and NMOS as pull down? It pulls up the output. Output na 1 ಮಾಡ್ತದೆ, ಇದು ಆನ್ ಆಗ್ತದೆ, ಇದು ಏನು ಮಾಡ್ತದೆ? 0 ಮಾಡ್ತದೆ. Okay, so I said the concept is very simple. If I make PMOS strong compared to NMOS, when this is strong, it will try to hold the output towards 1. PMOS strong ಆಗ್ತಂದ್ರೆ ಈ ಗ್ರಾಫ್ ಹೇಗಾಗ್ತದೆ ಅಂದ್ರೆ ಹಿಂಗಾಗ್ತದೆ. Output will stay at logic high for a longer time. ಯಾಕಂದ್ರೆ PMOS strong ಐತಿ. If I do reverse, NMOS strong ಮಾಡ್ಬಿಟ್ಟಂದ್ರೆ NMOS ಏನ್ ಮಾಡ್ತೈತಿ? ಲಘು ಲೋ ಮಾಡ್ಬಿಡ್ತೈತಿ output. So output ಹೈ ಉಳಿಯಂಗೆ ಇಲ್ಲ, ಲಘು ಲೋ ಆಗ್ಬಿಡ್ತದೆ. Here, say this is beta P by beta N, maybe 10 by 1. 10 times PMOS is stronger than NMOS. Therefore, output is staying for a longer time at logic high. PMOS logic high. So this graph is beta P by beta N is 1 by 1. That will equal. So it is medium. This graph, it is beta P by beta N. It is 1 by 10. And N is 10. Beta N is 10. Beta P by beta N is WP by WN. Directly, you can write. Okay. So here, in this graph, width of PMOS is 10 times more than width of NMOS. Second graph, both the widths are same. Third graph, left hand side, width of NMOS is 10 times greater than PMOS. So our transfer characteristics tells us that if I make PMOS more strong, output will try to stay logic high for a longer duration. Or if I make both equal, yes, almost they will be same. Or if I make NMOS more strong, output will try to stay at logic 0 for a longer duration. So we can play with the width of the MOSFETs and we can get the desired results. Okay. Perfunctory next topic is noise margin. Margin. Okay. So what is this noise margin and what do you understand from this? For understanding the noise margin, what we have to do, we have to take an example of two inverters connected back to back or in series. So this is inverter 1, this is inverter 2. Inverter 1, inverter 2, both are connected back to back. Fine. Say let me take an example that I am giving input 0 volts to this inverter. Fine. Due to some fault, I am getting output 4 volts. Now, this 4 volts is going to the input of second inverter. Okay. So this 4 volts is going to the input of second inverter. And what it should consider the 4 volts as? High or low? It will consider it as high. Okay. Suppose instead of 4 volts, if due to some fault, output of inverter 1 is 2.8 volts or 2.5 volts. 2.5 volts. Okay. Then what input should this consider? 2.5, it should consider it as low or high. Low or high. A great confusion. It's a great confusion. For inverter 2, if the input is 2.5, no, it's a great confusion for it. Should I consider it as low or high? Therefore, we have this concept of noise margin. Okay. Noise margin. So, actually, noise margin is can be defined as immunity of the circuit to the noise. Immunity of the circuit to the noise. Andre, how is the immune system of the circuit towards the noise? Now, just in here, due to some fault or say due to some noise, if it is taking 2.5 volts or it is giving 2.5 volts, then it will be a problem for this inverter. Therefore, to avoid such problems, okay, or simple words for health engineering, we have kept some level defined. E level was defined by 20. E level. E level. Suppose the output of first inverter is less than this level. Say this level is 3.5 for example. Okay. If this level is 3.5, and if the output of this first inverter is less than 3.5, then it will not consider that 3.5 as high. So we have defined the levels. If any voltage greater than 3.5, yes, that will be considered as logic high. And again I will get logic 0. In the same way, if I am giving 5 volts here, and due to some fault, actually next product will become output. In 5 volt output is 0. But if I am getting 2 volts, then again there will be confusion for this inverter. 2 now 1 to 0 some confusion. So to solve that, we have defined some level. Okay. Say 1.5. Example 1.5. 1.5 ಗಿಂತ ಕಡಿಮೆ ಇತ್ತಂದ್ರೆ yes, this will consider it as logic low. Okay, say it is 1.2. 5 volts input ಕೊಟ್ಟರೆ it is 0.22, but due to some noise is added which is creating or which is adding some signal to the original signal. So 5 is 0 badi 1.212. If this 1.2 or if this voltage is under this range, then it is a good circuit. Okay, this can be considered as yes, it is under the range. Okay, so there will not be any confusion. If output of this comes under in this range, then it is wrong. Then we may not get the perfect answer. Okay. It will create confusion. So to avoid the confusion, we have defined the range, and the output should be within the range. This range ಒಳಗೆ ಇರಬೇಕು. Okay. Understanding? So I have written few terms here. VOH minimum. Okay. H means high. VOL maximum. L means H means high. L means low. So what we are saying, output from the first circuit, okay, if it is high, OH, O andre output, H andre high. So minimum istare signal barbeku from the output one. Minimum istare signal barbeku. Actually 5 volts barbeku. High ಬೇಕಾದ್ರೆ ಎಷ್ಟು ಬರಬೇಕು full voltage ಬೇಕಾದ್ರೆ. If we are expecting high, then we expect 5 volts. But our noise margin, ಅದ್ರಾಗ ಏನು ಮಾಡ್ತೀವಿ ನಾವು, okay 5 volts ಬರತ್ತಿಲ್ಲ, fine. At least 4 volts ಬರಬೇಕು. Okay. In the same way, if I want low, what we expect, low ಅಂದ್ರೆ ಏನು expectation ಏನು ಇರ್ತದೆ, 0 ಇರ್ತದೆ. But at least 1 volt ಬರಬೇಕು. So this is it should come 0 volts, but maximum it can come up to 1 volts. ये कहते OL ಅಂದ್ರೆ output which has to be low. It has to be low. Maximum it can rise up to 1 volt. Hanga this is high. Okay, 5 volts irಬೇಕು, but at least minimum 4 volts irಬೇಕು. So output, high output, it should be minimum at least 4 volts. These two are defined for the inverter 1. Inverter 1 output is ಎರಡನೇ ಇನ್ವರ್ಟರ್ ನಾವು ಏನು ಮಾಡಿದ್ವಿ VIH ಮಿನಿಮಮ್ ಅಂದ್ರೆ I ಅಂದ್ರೆ ಇನ್ಪುಟ್, H ಅಂದ್ರೆ ಹೈ. ಸೊ ಈ ರೇಂಜ್ ಇಲ್ಲಿ ಇದೆ. Say 3 volts. This is 4 volts. This is 4 volts. This is 3 volts. So here for inverter 2 we are defining some range at the input side. VIH minimum ಅಂದ್ರೆ input for this inverter which is high, actually 5 ಇದೆ, but at least ಎಷ್ಟು ಇರಬೇಕು, minimum ಇರಬೇಕು 3 volts ಇರಬೇಕು. Then it will consider the output as high. 3 volts ಕಡಿಮೆ ಇತ್ತಂದ್ರೆ it is not considered as high. We may get garbage, we may get incorrect answer. So answer correct ಬರಬೇಕಂದ್ರೆ at least minimum ಇಷ್ಟೇ ಇರಬೇಕು. Minimum input voltage which is high, it should be at least this much. ಎಲ್ಲಿ ಬರುತ್ತೆ ಅಂದ್ರೆ ಇಲ್ಲಿ ಬರುತ್ತೆ. ಇನ್ನೂ ಒಂದು ಪಾಸಿಬಿಲಿಟಿ ಏನಂತ, ಇಲ್ಲಿ 4 ವೋಲ್ಟ್ಸ್ ಬಂದಿದ್ದ, ಇಲ್ಲಿ ಬರ್ತಾ ಬರ್ತಾ 3 ವೋಲ್ಟ್ಸ್ ಆಯ್ತು. ಈ ವೈರ್ದಾಗ ಏನೋ ಫಾಲ್ಟ್ ಇತ್ತು ಅಂತ ತಿಳ್ಕೊಳ್ಳಿ. ಈ ವೈರ್ದಾಗ ಒಂದು ಫಾಲ್ಟ್ ಐತಿ, ಇಲ್ಲಿ 4 ವೋಲ್ಟ್ಸ್ ಆನ್ಸರ್ ಬಂತು, ಬಟ್ ಬರ್ತಾ ಬರ್ತಾ ಇಲ್ಲಿ 3 ವೋಲ್ಟ್ಸ್ ಆಗ್ಬಿಡ್ತು. ಎಸ್, ಇಟ್ ಇಸ್ ವ್ಯಾಲಿಡ್, ನಡೀತದ. ಯಾಕಂದ್ರೆ ನಮ್ಮ ರೇಂಜ್ ಏನದ ಅಟ್ಲೀಸ್ಟ್ 3 ವೋಲ್ಟ್ಸ್. ಇದು ಬರ್ತಾ ಬರ್ತಾ 2.8 ಆಗುತ್ತೆ. It comes under this range. Okay, so overall ಏನು ಹೇಳ್ತೀನಿ ಅಂತಂದ್ರೆ ಎಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ನಡೀತದ, ದಿಸ್ ಇಸ್ ನಾಯ್ಸ್ ಮಾರ್ಜಿನ್. ಒಂದ ವರ್ಡ್ ಒಳಗೆ ತಿಳಿಬೇಕಂದ್ರೆ ಎಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ನಡೀತದ ವೋಲ್ಟೇಜ್ ಒಳಗೆ, ದಟ್ ಈಸ್ ನಾಯ್ಸ್ ಮಾರ್ಜಿನ್. ಇಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ನಡೀತದ, ಇಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ನಡೀತದ, ದಿಸ್ ಇಸ್ ನಾಯ್ಸ್ ಮಾರ್ಜಿನ್. ಇಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ನಡೀತದ. ಇಲ್ಲಿ ಔಟ್ಪುಟ್ 1 ವೋಲ್ಟ್ ಬಂದಿತ್ತು, ಓಕೆ, ಇಲ್ಲಿ 5 ಕೊಟ್ಟಿದ್ವಿ, ಇಲ್ಲಿ ಆನ್ಸರ್ 1 ವೋಲ್ಟ್ ಬಂದಿತ್ತು ಅಂತ ತಿಳ್ಕೊಳ್ಳಿ. ಇರೋ ಒಂದು ಫಾಲ್ಟ್ ಇದೆ. ಅದೇ 1 ವೋಲ್ಟ್ ಬರ್ತಾ 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 ಇಲ್ಲಿ ರೀಚ್ ಆಗ್ತಾ ಆಗ್ತಾ 2 ವೋಲ್ಟ್ಸ್ ಆಗ್ಬಿಟ್ಟದ, ನಡೀತದ. ಯಾಕಂದ್ರೆ ಇಟ್ ಕಮ್ಸ್ ಅಂಡರ್ ಮೈ VOL maximum. ಇಷ್ಟು ಮಟ್ಟ ನಡೀತದ, ನನಗೆ ಇಷ್ಟು ಮಟ್ಟ ನಡೀತದ. ಇಲ್ಲ ಅದು 2.5 ಆಗ್ಬಿಡ್ತಂದ್ರೆ ಈ ರೇಂಜ್ ಆಗಿ ಬರ್ತದೆ. ಅವಾಗ ನೆಕ್ಸ್ಟ್ ಇನ್ವರ್ಟರ್ ಕುಚಿತ್ತು. Okay, so ಎಷ್ಟು ವೋಲ್ಟೇಜ್ ಫ್ಲಕ್ಚುಯೇಷನ್ ಅಲೌಡ್ ಐತಿ, or your circuit is having immunity towards how much noise. Fluctuation ಅಂದ್ರೆ noise, ಅದು noise ಗೆ voltage variation ಆಗ್ತದೆ. Okay, that is noise margin. ತಿಳಿತೋ ಇಲ್ಲೋ? So actually when we design complex circuits, ಬರೀ ಎರಡು ಇನ್ವರ್ಟರ್ ಇರೋದಿಲ್ಲ, ಸಾವಿರಾರು ಇನ್ವರ್ಟರ್ಸ್ ಇರ್ತಾವೆ. ಎಲ್ಲರೂ ಒಂದು ಫಾಲ್ಟ್ ಆಯ್ತು, ಅಲ್ಲಿ ನಾಯ್ಸ್ ಮಾರ್ಜಿನ್ ಯೂಸ್ ಆಗ್ತದೆ. ನಾವು ಈಗೇನು ಬೋರ್ಡ್ ಮೇಲೆ ಒಂದ ಇನ್ವರ್ಟರ್ ಬಿಡಿಸ್ತೀವಿ, ಒಂದ ಇನ್ವರ್ಟರ್ ಹಿಂಗ್ ವರ್ಕ್ ಆಗ್ತೈತಿ. ಬಟ್ ಆಕ್ಚುಲಿ ವೆನ್ ಯು ಗೋ ಇನ್ ಟು ಐ ಸಿ ಗಳು ಎಷ್ಟೋ ಇನ್ವರ್ಟರ್ಸ್ ಇರ್ತಾವೆ, ಎಷ್ಟೋ ಸರ್ಕ್ಯೂಟ್ಸ್ ಬ್ಯಾಕ್ ಟು ಬ್ಯಾಕ್ ಕನೆಕ್ಟೆಡ್ ಇರ್ತಾವೆ. ಒಂದು ಆರ್ಡರ್ ಇರ್ತೈತಿ, ಆರ್ಡರ್ ಇಸ್ ಕನೆಕ್ಟೆಡ್ ಟು ಮಕ್ಸ್, ಮಕ್ಸ್ ಇಸ್ ಕನೆಕ್ಟೆಡ್ ಟು ಡಿಕೋಡರ್, ಡಿಕೋಡರ್ ಇಸ್ ಕನೆಕ್ಟೆಡ್ ಟು ಮೆಮೊರಿ. ಹಿಂಗ Okay, ಅಲ್ಲಿ ಏರ್ ವೋಲ್ಟೇಜ್ ಫ್ಲಕ್ಚುಯೇಟ್ ಆಗ್ತಂದ್ರೆ ಎಷ್ಟು ಫ್ಲಕ್ಚುಯೇಷನ್ ಅಲಾಟ್ ಐತಿ that is defined by noise margin. ಇದೆಲ್ಲ ಏನು ಎಕ್ಸಾಂಪಲ್ ತಗೊಂಡ್ವಿ ನಾವು ವೋಲ್ಟೇಜ್ ಲೆವೆಲ್ಸ್ ಜಸ್ಟ್ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಹೇಳಬೇಕಂದ್ರೆ ಒಂದು ಕೇಸ್ ತಗೊಂಡಿವಿ. Okay, those are fixed values, right? So noise margin is immunity towards the noise. Okay, we have a formula actually, NMH NML. NM ಅಂದ್ರೆ ಏನು? noise margin. H ಅಂದ್ರೆ ಏನು? towards high, ಈ range. So what is noise margin is difference between these two values. Difference between these two values is noise margin, which is towards high side, NMH. What is NML? Low side. So difference between these two, difference between these two levels. ಅಂದ್ರೆ ಇಷ್ಟು ವೇರಿಯೇಷನ್ ನಡೀತದ, ಇಷ್ಟೇ ವೇರಿಯೇಷನ್ ನಡೀತದ, ಇದಕ್ಕಿಂತ ಹೆಚ್ಚು ವೇರಿಯೇಷನ್ ನಡೆಯಂಗಿಲ್ಲ, ಈ ರೇಂಜ್ ನಾಗ ನಡೆಯಂಗಿಲ್ಲ. So NMH is nothing but, you can note down the formula, VOH minimum minus VOH minimum minus VIH minimum, or you can have a mod. You can have a mod. Actually, the thing is mostly VIH minimum minus VOH minimum. Allah, one second. Yeah, correct. VOH minimum minus VIH minimum. NML is equals to VOL maximum. ಯಾವ ಮ್ಯಾಕ್ಸಿಮಮ್ ಐತಿ ನೋಡ್ರಿ, ಅದನ್ನ ಮೈನಸ್ ದೊಡ್ಡ ಮೈನಸ್ ಅಂತ ಮಾಡ್ಬೇಕು ಯಾವಾಗ. ಇದು ಹೈಯರ್ ಲೆವೆಲ್ ಐತಿ, ಸೊ ದಿಸ್ ಮೈನಸ್ ದಿಸ್, ಇಲ್ಲಿ ದಿಸ್ ಮೈನಸ್ ದಿಸ್. ವಿ ಎರಡು ಸೇರ್ ಬರೋದಲ್ಲ, ಇದು ವಿ ಓ ಎಚ್ ಸಾರಿ ವಿ ಓ ಎಲ್ ವಿ ಐ ಎಲ್ ಇದೆ, ಸಾರಿ ಇದು ವಿ ಐ ಎಲ್. ಇದ್ರಾಗ ಕನ್ಫ್ಯೂಷನ್ ಇರ್ತದೆ ಬಹಳ. ಓ ಎಲ್ ಬರೀರಿ, ಐ ಎಲ್ ಬರೀರಿ, ಎಲ್ ಎಲ್ ಬರೀರಿ, ಎಚ್ ಎಲ್ ಸ್ಟಾರ್ಟಿಂಗ್ ನನಗೂ ಕನ್ಫ್ಯೂಸ್ ಆಗ್ತದೆ. ಇಲ್ಲಿ ನೋಡ್ರಿ, ಓ ಎಲ್ ಬರೀತೀರಿ ಔಟ್ಪುಟ್, ಐ ಇನ್ಪುಟ್, ಇಲ್ಲಿ ಇನ್ಪುಟ್ ಐತಿ, ಇದರ ಔಟ್ಪುಟ್ ಇಲ್ಲಿ ಇನ್ಪುಟ್ ಹೋಗ್ತದೆ. ಸೊ ಇಲ್ಲಿ ರೈಟ್ ಸೈಡ್ ಐ, ಲೆಫ್ಟ್ ಸೈಡ್ ಓ. ಎಚ್ ಎಲ್ ಬರೀತೀರಿ ಮೇಲೆ ಐ, ಲೋ ಎಲ್ ಬರೀತೀರಿ ಕೆಳಗೆ. ಓಕೆ, ಸೊ ಇದು ಔಟ್ಪುಟ್ ಐತಿ, ಔಟ್ಪುಟ್ ಫಸ್ಟ್ ಇನ್ವರ್ಟರ್. ಸೊ ಓ ಎಚ್ ಐತೋ ಎಲ್ ಐತಿ, ಎಚ್. ಇದು ಐ ಐತಿ, ಇನ್ಪುಟ್ ಆಫ್ ಸೆಕೆಂಡ್ ಇನ್ವರ್ಟರ್ ಐತಿ, ಎಚ್ ಐತೋ ಎಲ್ ಐತಿ, ಎಲ್. ಸೊ ದಿಸ್ ಇಸ್ ವಿ ಐ ಎಲ್. VIL maximum minus VOL maximum. Mod of VIL maximum minus VOL maximum. This is the concept of noise margin. So next topic is body effect. Okay, body effect. What is body effect? What is body? Yes, sir, body. Body alla. ಇಲ್ಲಿ ನಾವು VLSI body ಅಲ್ಲಿ. Body is also called as substrate or bulk. Body is also called as substrate or bulk. Okay. So here, what is body effect is? It is the effect of the body if it is connected to different things. For example, I have an inverter Now here noting is that this is input, this is ground. So this is input, this is output. Okay, this is ground, this is VDD. Now, here consider that the body of the P MOSFET should be connected to highest potential, and body of the NMOS should be connected at the lowest potential. Even now, not even. Okay. But if we don't do that, okay, either there will be some difference of potential. Okay. Or by doing this, what happens is the threshold voltage of this MOSFET will change. Threshold voltage is VT, and then device turning on. So ಯಾವ ವೋಲ್ಟೇಜ್ ಡಿವೈಸ್ ಆನ್ ಆಗ್ತಿರ್ತಲ್ಲ ಅದು ಚೇಂಜ್ ಆಗಿರ್ತದೆ. 0.7 ಗೆ ಆಗುದಿಲ್ಲ ಈಗ. ಸ್ಟಾರ್ಟಿಂಗ್ ಇಟ್ ವಾಸ್ ಟರ್ನಿಂಗ್ ಆನ್ at 0.7. If I do wrong connection, it will not turn on at 0.7. It will change 0.72 or 0.68, something change ಆಗಿರ್ತದೆ. Actually ಜಾಸ್ತಿ ಆಗ್ತದೆ as per this equation. So what is this equation is? ಈ equation ಏನು ಹೇಳ್ತದೆ ಅಂದ್ರೆ VT is the new threshold voltage. Wrong connection ಮಾಡಿದ್ರೆ ಅಂದ್ರೆ new threshold voltage which is given by old threshold voltage. ಮೊದಲು ಇಷ್ಟಿತ್ತು, ಕರೆಕ್ಟ್ ಕನೆಕ್ಷನ್ ಮಾಡಿದ್ರೆ ಇಷ್ಟಿರ್ತದೆ. Wrong connection ಮಾಡಿದ್ರೆ old threshold voltage plus something is added. What is added? This is body effect parameter. This will be small, very small. Actually, pura variation not under this. Okay. This is gamma into root of 25 plus VSP. 25 plus VSP. What is VSP? Is source to bulk voltage. Vs minus Vb minus root of 25. So if by chance Vsb is 0 is the root. Our character 0 is the root of 25 minus root of 25 0 into gamma 0. So you have to save out. Suppose if this is non-zero, then something will be added to the original value. This is nothing but body effect. So what is body effect in one sentence? Body effect in one sentence is if we change the connection of the body at some different point, there will be a change in the voltage VSB. That change in voltage will add some voltage to the original value of threshold voltage. So by changing the connection of body, threshold voltage is changing. This effect is body. By changing the connection of the body to some other terminal, threshold voltage of the device itself is changing. That is body effect.